Electricity is a naturally occurring phenomena in the universe. Much like water, we know quite a lot about it. We know its characteristics, and we can calculate and predict its response to a given set of circumstances. And just like water, without guidance and control, it will flow wherever it wants to until it is balanced and equalized. Electricity is everywhere and is a part of everything, and I mean everything. If you want to prove that to yourself, scuff your shoes over the nylon carpet, then touch the doorknob. There's a spark, and you'll get a shock. We've all had that happen. Another example, rub a balloon on your shirt a few times, and then put it on top of your head. Your hair will come up against it, and it'll stick to you. We call this static electricity, and they are two examples of the electricity that is a part of everything in the universe. So the question you might ask is, why do we get a shock, and why does the balloon stick? We actually know those answers, but we need to ask a more basic question first. Just what is electricity? In its simplest, easy-to-understand term, electricity is the flow or movement of electrons from one atom to another. It happens all the time, constantly, throughout the universe. And here's what I mean by that. Here's a picture of an atom. Stabilized atoms are composed of an equal number of electrons, protons, and neutrons. The protons and neutrons form the core of the atom, and the electrons orbit around the core. Protons and electrons are like a magnet. A magnet has a north pole and a south pole. For this discussion, we can refer to those as its magnetic charge, positive and negative. It's the same with electrons and protons. A proton has a positive charge, like the north pole of a magnet. An electron has a negative charge, like the south pole of the magnet. And just like the magnet, opposite charges attract each other, and like charges repel each other. That's one of the characteristics of electricity. As far as we know, everything in our universe is composed of atoms. So, if electricity is the movement of electrons, then electricity, or at least the potential for it, exists everywhere in the universe. Now, as I mentioned earlier, electricity is like water. They both seek equilibrium. We know that if we connect two tanks of water together, one containing more water than the other, water will naturally balance itself so that each container holds the same amount of water. Electricity does the same thing. If an electron is knocked from its orbit, an imbalance is created. One atom is missing an electron, and the other atom has an excess of electrons. This can be referred to as potential. When there is a greater potential in one thing than the other, the laws of nature call for an adjustment to rebalance everything. Unless you confine it, electricity will spread itself around to maintain an equal balance. With water, we direct it using a hose. With electricity, we direct it using a wire, which we call a conductor, because it will conduct electrons from one end of the wire to the other. When we walk, the friction of our shoes against the flooring forces electrons from their orbit, creating a potential. Using a supermarket example, the rubber sneakers you're wearing effectively prevents the electrons from rebalancing back to the floor, or to ground as it's called. Holding onto the plastic handle of the cart blocks their other escape route. What's happening is you're becoming negatively charged with excess electrons. When you reach out and touch another piece of metal, the shock comes. Reaching for the metal creates a new path to balance the universe. And you don't actually have to touch it. You just have to get close enough. The need to rebalance and diminish that potential is so great, electrons will jump across space to do so. That's the spark you see, the shock you feel. Here's another example. It starts with a clear blue sky day. Then the clouds come in, then gather, growing darker. They're rubbing together, building up an excess of negative electrons. When the charge becomes too unbalanced, the electrons will seek out matching protons, in this case, the Earth, the ground, to rebalance themselves. We call it lightning, electrons urgently jumping through the air to reach the ground. The sound we hear is the air molecules crashing back together to fill in the hole, the vacuum, created by the bolt of lightning forcing a path through the air. So that brings us to conductors. It takes a tremendous number of electrons to create the typical lightning bolt. It needs that power to bridge the gap for rebalancing. However, on a practical level, for us to harness electricity, we need something more manageable. Thus, the wire conductor. We've discovered that metal conducts electricity better than paper, or wood, or rubber, and we have come to rely upon certain materials, like rubber and plastic, to block the free flow of electrons to protect us from harm. But remember, with enough potential behind it, think of lightning bolt. Everything will conduct electricity, including your rubber sneakers. Since the early days of its discovery, we have since discovered how to generate electricity and to harness it for our use. Next, let's take a closer look at what's happening when electricity flows through a conductor. Let's go back to the atom. Remember, the electron is displaced, creating a flow of electricity. In this example, we force an electron into the conductor. The pressure needed to force the electron into the conductor is called voltage. As the electron is pushed in, an electron in the first atom is forced down the line to its neighbor. That neighbor in turn forces an electron onto the next, and so on in sequence until an electron comes out the other end. This is the flow of electricity. The number of electrons forced into the conductor at any instant of time is the volume. Like water, it's referred to as the current. The official designation is amperes, or amps for short. The atoms that make up the conductor itself have a natural resistance to being forced about in this fashion. That's called resistance, which is measured in ohms. So to state it properly, it will require 1 volt of electrical force to push 1 amp of current through a conductor resisting the conduction by 1 ohm. The standard household current at the wall outlet is typically 120 volts. The typical volume of current that can be drawn from that outlet, following standard wiring specifications, is 15 amps. The number of amps that can flow is dependent upon the size of the conductor used to supply the outlet. The larger the gauge of wire, the more amps that can flow freely and safely. There are limits, of course, and the ambient surrounding environment is one of them. Here's a quick chart with those specifications for a 120 volt source within an environment no hotter than 140 degrees Fahrenheit ambient. Just take note that the conductor tries to resist the movement of electrons through it. The result of this resistance is heat. Trying to draw too many amps through a conductor that's too small to support it will result in heat, melting of the wire, and a fire inside the wall of your house. Pay attention to the standards. It's important.